Okay, we're going to switch over to our last presenter, Arjun Singh from the University of California, Berkeley. Arjun received his BS in Electrical Engineering and Computer Science from the University of California, Berkeley. He is now a PhD student and an NDSEG fellow at Berkeley, where he works on robotics and computer vision. The title of his presentation is Apprenticeship Learning for High-Performance Helicopter Flight. For many robotic systems, human operators still significantly outperform autonomous operation. Apprenticeship learning is a new approach to high-performance robot control based on learning for control from ensembles of expert human demonstrations. In this talk, Arjun will present the theory of the apprenticeship learning algorithms, as well as experimental results in autonomous helicopter flight. Apprenticeship learning has enabled the most advanced helicopter aerobatics to date, including maneuvers such as chaos, tick-tocks, and auto-rotation landings that only exceptional, expert human pilots can fly. Arjun, thank you.
Thank you. Okay, so yeah, I'm Arjun Singh, and my advisor at Berkeley is Peter Abil. So the work I'll be describing today was started at Stanford, where my advisor collaborated with Adam Coates, Andrew Ng, Morgan Quigley, and Tim Hunter. And then when he became a professor at Berkeley is when I started working on the project, where we collaborated with Jay Tang and Nimbus Gohausen. Okay, so what makes this a hard problem? So first off, the dynamics of helicopter flight are unstable. And what that means is that when a pilot is flying a helicopter, if they took their eyes off the helicopter for more than a couple seconds, it would probably just crash. The pilot has to be continuously providing controls and continuously responding to what's going on with the helicopter. On top of that, helicopters are nonlinear and have complicated dynamics. So we can't model everything that's going on with the helicopter. There's a complex airflow going on. There's coupling between different parts of the helicopter. There's the dynamics of the blades that flex as it flies. And furthermore, all we get are noisy estimates of the state of the helicopter, including the position, the orientation, the velocity, and the angular rate. And for some maneuvers, we also have sensors for the blade and engine speed. Okay, so even though helicopter flight is a very challenging problem, there have been some success stories. And so some examples are listed here on this slide. The control techniques used for these success stories, I guess, are inner and outer loop PID control. And sometimes those are hand-tuned, sometimes those are automatically tuned. There's H-infinity control, LQR, and many other techniques. However, these successes have only been in the hover and forward flight regime. So either the helicopter is hovering or it's flying forwards. It's not doing anything more complicated than that. So here's an example result of that. So this was achieved by Andrew Ng and his collaborators in 2004. And this isn't an image. The video is actually working here. This is just a very, very good hover. And so this is great, especially for an autonomous helicopter. This is really, really good for a human. So let's see another example. This is also done by Andrew Ng and collaborators. So you see it hovering. Then if you look more closely, you'll notice it's actually hovering upside down. Okay, so now we've shown two impressive examples of what's been done. And so now, we can hover it upside down. So what about flipping it upside down? So in that video, what happened was the pilot flipped it upside down and then handed control over to the computer. And the computer did a great job of hovering. But the computer couldn't actually flip it. And so they decided to use the same techniques they used for the inverted hover to try to get it to flip. And so to do that, they first had to specify a trajectory. For hover, the trajectory is very simple. You don't want the helicopter to move. For flipping, we have to say, okay, we want it to stay in place and flip upside down, and maybe we'll do that a couple times. Okay? And so let's see what happened when they tried to hand engineer a trajectory and use the same techniques to follow that trajectory. So you see the helicopter flip. It's moving kind of a lot, more than you might want. And then it's taken to its limits. The engine dies, and the helicopter crashes. And like I said, the technique used here was essentially the same thing that was used for those hover examples I showed you. And so it's clear that the same techniques don't work here. And the way the model was generated here was a very typical way of finding a model for helicopters. And so what you do is you take the control inputs, you sweep them at a range of frequencies, and you run a regression to get the model out. And I'll go into more detail about that later. But there's nothing that fancy going on here. Just want to say that those methods don't work out of the box. Okay, so what's different? So we're talking about aggressive non-stationary regimes here. And so what success stories were there in these regimes? And so perhaps the only real success story before our work was by Gavrilets, Martinez, Metler, and Ferron in 2002. And what they did is they had their helicopter autonomously fly 3 maneuvers: a split S, snap axial roll, and a stall turn. And if you're not familiar with those maneuvers, you'll see video of some of these later. And how do they do this? So what they did is they had their human expert fly these maneuvers. Then they meticulously analyzed what the human expert was doing, how the human compensated for different types of error, and they hand-engineered controllers to emulate what the human does. And it worked very well, but it was extremely time-consuming. And there's a reason that they stuck to these 3 maneuvers and they didn't go to the full range of what the pilot could do. And that's simply that there wasn't enough time. So we're going to start with the same learning point here with our method. We're going to have a human expert give demonstrations. The difference is that we're not going to have to hand-analyze anything. The algorithm will do that for us. So the human flies something, and then we can fly the same thing. And what I'll go through in this presentation is I'll show you that this method generalizes to a wide range of aggressive maneuvers. It can execute them in rapid succession. And like I said, we start at the exact same point as these hand-engineered controllers did. Okay, so what's so different about stationary flight versus aggressive flight? Why is this so much more difficult? So with hover and the stationary flight regimes, it's much easier because you can focus on that single regime. And that enables you to do things like collect a lot of data. So that data I told you that we collected with the frequency sweeps, we could just do that for 10 minutes, an hour, 3 hours, whatever, and it's all for the exact same regime, right? And that lets you get a very, very good model for that regime. So what are we collecting? We're collecting the control inputs that the pilot is giving, and again, the position, orientation, velocity, angular rate. And then we build a model and a model-based controller from those. So the model-based controller actually works in these regimes because we have enough data and because it's not changing. So why can't we do that technique? Why can't we use the same technique for the aggressive flight regimes? So first off, you just can't collect that much data to get that high fidelity of a model for the entire flight envelope that you're considering, right? Before, we were only considering the hovering situation, and now we want to consider doing flips and stall turns and loops and all those things, and we just don't have, it's infeasible to collect enough data in a reasonable amount of time.